Hello statistics students. I am going to prepare for you 2 video lectures about chapter 9 to help get you ready to do your homework on that chapter, which is already posted and is coming up due next week. And so this is a chapter about multiple linear regression, and like your other chapters, you have a group homework and an individual homework, but you'll have to work on the group homework by video chat or some other mechanism. But I think you can do it. There's only one problem that's a group problem. I will post the script for the analyses that I'll show you now on Canvas in this latest module. So you'll have those available to you. And the PowerPoint I'll post with this announcement with the lecture, and it is a Google Doc. So you can look at the PowerPoint, and I'm going to look at the PowerPoint to refer to different slides. So I'm going to start with the first slide in the PowerPoint, which is what multiple linear regression is all about. So multiple linear regression, the idea here is you take the basic idea of simple linear regression, where you have a numerical response variable and a numerical predictor variable, and now you add more than one predictor variable. So the idea is like you have a response, like for example the number of flowers that a plant makes, and you know that that response is not just controlled by one thing, it's probably controlled by more than one thing, and you want to make a model that accounts for more than one thing that might be controlling your variable. So if you were looking at flower number, you might be looking at like nutrient levels in the soil and the amount of water it's been given, and maybe the amount of pollinators that were present. So you'd be looking at these multiple variables. And we have 2 examples we'll walk through that mirror the ones in the textbook. I'll walk through one in this lecture and then one in the next lecture so that it's not like too much all at once. So the first example is this meadow foam example. Meadow foam is a beautiful flower that people are interested in using because you can make oil out of the seeds, kind of like canola oil or rapeseed oil. You could potentially use this for cooking, or you could use it for like making biodiesel or whatever. But in order to have seeds that might have oil in them, you have to have flowers, because flowers eventually make seeds. So this study was looking at how these different treatments and how the meadow foam was grown affected the number of flowers it made. So I'm on slide 3. You can see meadow foam is super cute. Let's go to slide 4, where we can see the response variable is going to be how many flowers there were. This is a numerical variable. One of their predictor variables is light intensity, and they've experimentally manipulated how intense the light is that the plants are getting. And they have 1, 2, 3, 4, 5, 6 levels of that. You could treat it as categories, or you could treat it as numerical, and it makes more sense to treat it as numerical because it's a more powerful analysis, and it does look like the relationship is linear. They also have a timing of when the plants were given light, so an early start and a late start. And it looks like overall, if we look at the graph, the early start is the green points. It looks like they're making more flowers when the plants are started earlier. So that's the basic scene here. We can look at the graph and we see that maybe there's 2 separate lines that run through the points. Maybe there's a line that runs through the orange points and a different line that's a little bit higher that goes through the green points. And we would like to make a model that allows us to model these 2 different lines. So let's go on to slide 5. The first line here is the code for my model. And this is the most complex model I could make with this data set. So I have here a linear model, and I have flowers as my response variable. I have the intensity of the light as one of my predictors. I have the timing, which is early or late. Now this is an interesting example where timing is really a categorical predictor here, but we learned last week when Dr. Ch9 was lecturing that we can treat these categorical variables as 0s and 1s, so as numeric. So in this particular data set, they're coding the late start plants as a 0 and the early start plants as a 1. So I can put that in my first line in my model. So I have my model as flowers is modeled by intensity, time. So that's as a factor because there's just two levels of it. And then this last term, this intensity colon time bit, that is saying that I think it's possible that the effect of intensity of light depends on the timing of when the plants were started. So that's called an interaction term, and it means these two variables, the effect of one might depend on the level of the other. Like maybe light intensity doesn't matter if you start it too late because the plants are dead anyway. There's totally reasons why this could be a thing. So in our fullest model, we include that potential interaction. The second line is going to look at the residuals plots to see whether my assumption of equal variance is met. And then I'm going to look at my model summary. So let's go on to slide number 6. Cool. This is my residuals plot. So I am looking at this plot to see whether the equal variance assumption is reasonable here. And as I look along this plot, I think it looks pretty okay. So the experimental design demonstrated that independence was met. This plot makes me think equal variance is reasonable. I haven't done a formal test for normality. That would be a good thing to do, but we're not going to do that right now. So if this was a homework problem, that would be a good thing to do. Do a Shapiro's test or look at a QQ plot and see how reasonable normality is. And that would be most important if you wanted to interpret the confidence interval around the lines. So we're okay with our model assumptions for now. We're going to run our full model, and the output is on slide 7. So if we look at this model, we can see the intercept is significantly different from 0. The light intensity definitely looks like it matters, and it looks like there's a negative relationship between flowers and light intensity. So these plants don't make a lot of flowers if it's super, super, super bright light. Then the next factor is time, and then the last one is the interaction between time and intensity. And it looks like neither of these are significant in this model. We have a p-value for time of 0.075 and a p-value for the interaction of 0.906. So there's really no evidence for that interaction term. We can look at the r-squared. I usually look at the adjusted r-squared. That penalizes for having a more complex model. When I report it, I'll say I'm reporting the adjusted r-squared. So based on this r-squared, we can say that this model represents 77% of the variability in flowering in the meadow foam plant. That's cool. And then the last part of this is actually stating the model. So this last part says that my model statement, my equation that I got out of this would be that the average number of flowers equals 71.62 minus 0.041 times the intensity of the light, plus 11.5 times time. Now when we're talking about the late ones, time is 0, so that term wouldn't be part of the model for the late ones. And the early ones, time is 1, so that would be part of the intercept for the early ones. And then the last term is this plus 0.0012 times time times intensity. Now with the late flowers, time is 0, so that term doesn't contribute to the model. With the early flowers, that term changes the slope. It would say that the slope is actually slightly higher for the early flowers. But we also know that it's not significant by looking at the p-value, which is 0.9096. So that's our model statement, and we could use that to predict the average number of flowers at any light intensity or timing. Okay, so we're going to move on to slide number 8. This is really focusing on the interaction. So the interaction, a definition of the interaction would be when the effect of one variable depends on the level of the other variable. Like if this were true, if the effect of intensity depended on the timing, it wouldn't make sense to say anything about intensity just all by itself, because the effect of intensity depends on the time. So you would say, if you start the flowers early, intensity affects the flowering this way, and if you start the flowers late, intensity affects the flowers in a different way. So when we look at our model here, the second line is the model that we looked at on the last slide. We see that the coefficient for that interaction term, the 0.0012, is quite small. And we know that the p-value was quite large, it was 0.9. So there's really no evidence for this interaction. There's no evidence that it is needed or makes the model better. The best thing to do next is to take it out of the model and rerun it, because you're kind of wasting degrees of freedom and making your life more complicated by including this term that's not significant. So that's what we're going to do. We're going to go on to slide 9. I took it out. So what you can see if you look at my model formula, this LM formula equals flowers tilde intensity plus factor time, is I don't have that term with the colon in it, which means I'm not interested in looking at the interaction anymore. So then we look at the output from here, and the thing that's cool is now time is significant. So before, time wasn't significant because we were building a less powerful model by incorporating these things that were not significant. So here our p-value for intensity is 1.04 times 10 to the negative 7, so that's definitely statistically significant. And our p-value for time is 0.000146, so that is also significant. We would keep them both in the model. It looks like the model explains 78% of the variance. Interestingly, this simpler model explains slightly more of the variance. So it's a better model, or it's about the same in terms of the amount of variance, but it's simpler. If you can explain the same amount of variance with a simpler model, this is good, this is better. So then up on the right, we have the model statement. So this is the formula that the model is explaining. It's saying the mean number of flowers equals 71.31 minus 0.04 times intensity plus 12.16 times time. Now time is 0 for the late start plants, and if you look at the graph below that, you can see that the line that goes through the orange points is lower, and then time is 1 for the early start plants, which means they have a higher intercept but the same slope. They would have a different slope if they had a significant interaction. They didn't have a significant interaction, so we dropped it, but they have a higher intercept, and then so you can see the dotted line that goes through the green points, it has a higher intercept. So that's our model statement here. And I think we'll be done with this example, and I'll give you another video in a few minutes with the next example from the chapter. If you have any questions or comments, please feel free to send me an email or discuss amongst your group that you're doing your homework with, or post in the discussion on the Canvas site. Anything you need to do, I want to make sure you can get these last few chapters as we work through finishing the semester online. Okay, so sign off now, and I'll give you another video on the next section.